Programming is the art of creating instructions for computers to follow. It's how we build everything from apps and websites to robots and video games. Programmers are the architects of the digital age. They design and build the software that powers our everyday lives, making tasks easier, faster, and more efficient. Ready to dive in? Start your coding journey today and shape the future.
Welcome to Java, the powerhouse of programming. Java is a widely used programming language for coding web applications, services, big data, and all. Java is a multi-platform, object-oriented, network-centric language that can be used as a platform in itself. It's renowned for its platform independence, advanced security, inbuilt functions and libraries, and rock-solid reliability. Unlock endless possibilities with Java. Start coding with us today.
A compiler translates your entire source code into machine language at once, making execution super fast. But an interpreter translates and executes your code line by line, perfect for scripting languages like Python. On the other hand, Java is unique because it uses both compiler and interpreter.
Ever wondered how your Java code turns into a running application? First, you write your Java code in a.java file. The Java compiler translates this into bytecode. The JVM takes this bytecode and translates it into machine code that your computer can understand. The JVM has class loader, which loads the bytecode file, and bytecode verifier to ensure it's safe. The just-in-time compiler optimizes it, and execution engine runs it to the operating system.
Today, we'll write our first Java program. Import java.util**. This line imports all classes and interfaces from the java.util package in Java. Public class Hello World. This line declares a public class named Hello World in Java. Public static void main string args. This line defines the entry point of Java program, with a method named main that takes an array of strings as argument. System.out.println hello world. This line will print hello world to the console in Java. Let's compile and run the program.
Today, we are talking about variables. A variable in Java is a container that stores data values. Let's say, for example, here, the variable name is number, which stores a value of 10. The main use of variable is to store data values like number, text, or other information.
There are two main types of data types in Java, which are primitive and non-primitive types. Primitive types include int, float, double, char, and boolean. Non-primitive types include string, arrays, and classes. These are more complex structures.
Today, we will learn about operators. In Java, operators are symbols used to perform operations on variables and values. From arithmetic to logical, Java offers a wide range of operators to manipulate data. That's all about operators. First up, we have arithmetic operators. These are used to perform basic mathematical operations in Java. For example, addition, subtraction, multiplication, etc. Next is relational operators. These are used to compare values in Java. With relational operators, we can determine if one value is greater than, less than, equal to, or not equal to another. Moving on to logical operators. These are used to combine multiple conditions in Java. For example, and ensures that both conditions are true, or ensures that at least one condition is true, and exclamation negates a condition. Let's see how we can swap two numbers without using a third variable. First, we define our main method in a class named swapNumbers. We have two variables, a and b, with values 5 and 3. Now, let's swap their values using arithmetic operations. First, add a and b, store in a. Then, subtract the b from new a, stored in b. Finally, subtract the new b from new a, stored in a again. After swapping, a is now 3 and b is 5. And that's how you swap two numbers without a third variable in Java. Today, we will learn about the scanner class in Java. The scanner class is part of the java.util package, which allows us to read input from the user. Let's take a look at a simple example. Here, we create a scanner object called sc and pass system and as an argument, which represents the standard input stream. We can then use methods like nextLine to read a line of input from the user. For example, if we want to read a user's name, we can use the nextLine method like this. The input is then stored in the username variable.
People make enormous number of choices every day, and so does the computer, and that's where conditional statements comes in. The deciding factor between what it does and what it doesn't is usually dictated by a condition. For example, a user tries to access a computer. If the password is correct, the user can access it. If it's not correct, user has to retry again.
We will learn about conditional statement in Java. In Java, conditional statements allow us to make decisions in our code based on certain conditions. Let's start with the if statement. The if statement executes a block of code if a specified condition is true. Next, we have the if-else statement. The if-else statement executes one block of code if the condition is true, and another block if the condition is false.
In else-if statement, if the condition is true, the corresponding block of code is executed. If the condition is false, the program moves on to the next else-if statement or the else statement, if present. Let's understand it with an example. Here, if x is greater than 0, it's positive. Else, if x is less than 0, it's negative. Else, when all the conditions doesn't satisfy. X equals 0.
Today, we will learn about switch statement in Java. Switch tests a variable against multiple values. Each case represents a potential value. Let's understand this with an example. Always use break to avoid fall-through, which means executing the next case unintentionally. Here, day is 3. Therefore, it will print Wednesday. If we write the case without break, this prints Monday. Tuesday on day value is 1. On other hand, default handles any unmatched cases.
Loops are fundamental constructs in programming that allow you to execute a block of code repeatedly based on a condition. Imagine you're baking a batch of cookies. Instead of cutting out one cookie at a time, you repeat the action until all the dough is used. That's what loops do in programming. Repeat tasks until a condition is met.
Today, we will learn about for loops in Java. A for loop helps you to repeat a block of code a certain number of times. Here's the basic syntax. First, initialize a variable, usually an integer. Next, set a condition to check before each loop iteration. Finally, update your variable after each loop. This loop starts at 0, runs while I is less than 10, and increments I after each run, printing values from 0 to 10.
A while loop repeats a block of code as long as a condition is true. Let's take the previous example of dough to cookies. Imagine you need to scoop dough until the tray is full. In Java, we can use a while loop to do this. The loop continues scooping while there's dough left. Each time, it decreases one portion and increases one cookie. When dough left is 0, the loop stops.
Today, we will learn about do-while loops in Java. A do-while loop ensures the code block runs at least once. Here's the syntax. First, the code inside the do block runs. Then condition is checked. This prints number 1 to 5. The loop runs until the condition is false.
Nested loops are loops inside other loops, useful for tasks like creating grids and multidimensional data. Let's take an example. Here, the outer loop runs 3 times, and for each iteration, the inner loop also runs 5 times, allowing it to travel through each element. This creates a 3 by 5 grid of coordinates.
Today, we will learn about printing a start pattern in Java. Let's create a star pattern like this. First, we need a loop to handle the number of rows. Let's use 5 rows. For each row, we need another loop to print stars. The number of stars equals the current row number. After printing stars for a row, we move to the next line. Hence, we observe number of rows equals to number of stars. Let's get into code. First, set up your main method. Creating a loop for the number of rows. Inside, creating another loop for the stars. Add a new line after each row. Hence code gives the pattern.
Let's create a triangle star pattern in Java. Here n is the number of rows, that is 4. In the first row, we have 3 spaces and then 1 star. In second row, we have 2 spaces and 3 stars. In the next row, we have 1 space and then 5 stars. So we can say, spaces are decreasing by n minus I. And stars are increasing by 2 into I minus 1 for each row. Let's get into code. Here, number of rows is 4. The outer loop runs from 1 to n, where n is the number of rows. The first inner loop prints spaces to center the stars. The second inner loop prints stars, forming the triangle. This creates a triangle pattern from stars. In previous section, we have learned that variable is a container that holds a certain type of value. What if I tell you to arrange these containers in a row, having a same name and having same type of values? Yes, that is an array. This data structure can store multiple values of same type efficiently. Each container has an index starting from 0. You can access elements by their index, like number of 0, for the first element.
In previous session, we have learned about what is array. Now we're gonna learn about 1D array. It is a collection of elements stored in a single row. Think of it as a list of items, like your shopping list, where each item has an index starting from 0, 1, 2, 3, 4, 5. Using a 1D array when you need to store multiple items of same type and matches them using an index. It's perfect for handling a fixed number of elements efficiently. In Java, we declare a 1D array by specifying the data type, followed square brackets, and the array name. Then we allocate the memory for the array using the new keyword.
Let's learn how to use 1D arrays with an example. First, we declare and initialize an array to hold 5 integers. Here the new keyword allocates memory for the array elements. Then we use a for loop to assign values to the array. Inside this loop, each element is twice as its index. Then we take another for loop to print each element in the array with its index. You can see the output of this code.
In the previous session, we learned about 1D array. If we add more rows to our single D array, we will end up with a 2-dimensional array or 2D array. Imagine it as a grid, like a chessboard, where each position is identified by 2 indices. A 2D array is like a table with rows and columns, where each cell holds an element. It is used to represent data in a matrix form. In Java, we declare a 2D array by specifying the data type, followed by 2 sets of square brackets, and an array name. Then you allocate memory for the rows and columns using the new keyword.
Let's code for 2D arrays in Java. First, we declare and initialize a 2D array with 3 rows and 4 columns using the help of new keyword. Then, we use nested for loops to assign values to the array. Each element is the sum of its row and column indices. Then, we take another set of nested loops to print each element of the array in a grid format. This will print the elements in a 3 by 4 grid format, showing how 2D arrays are structured.
Let's talk about methods in Java. Think of a method as a recipe for making lemonade. You need two things: water and lemon juice. These are your parameters. You pour the water and lemon juice into pitcher. The method mixes them together to create lemonade. The result is the lemonade you can drink. In Java, a method works the same way. You provide inputs, called parameters, and the method processes them to give you a result. Using methods makes your code reusable and organized. Let's understand parameters with an example. Our JuiceMaker class has a makeJuice method that takes a string parameter representing the fruit. Parameters are like placeholders for the values you pass to a method. Arguments are the actual values you pass to the parameters when you call the method. In this case, apple and orange is our argument, and fruit is a parameter. We can pass our arguments while calling the methods from the main function inside the main class like this. Let's look into the method using a simple example. Here method sum is the class. It has a method name addNumbers that takes two parameters a and b, which adds them and returns the sum. In the main method, we create an instance of method SumObj and call addNumbers with two numbers and print the result. Here number 1 is a and number 2 is 27, and the result is 100. That's how method use in Java to perform task efficiently. So, what is a return statement? It's like the result of a method. When you ask a question, you expect an answer, right? Similarly, when a method completes its task, it can return a value back to where it was called. Let's take an example of microwave. We put the item inside, and it bakes it. Here, microwave is the method that returns a string value depending on the argument. Now, let's see it in action. Here, we are calling the method microwave using bakerObject while passing a string argument brownie. Then the method checks the condition and returns the string chocolate brownie, stored in baked item variable. Today, we're talking about variable arguments in Java. Variable argument allow a method to accept 0 or more arguments of a specific type. Here's a quick example. Here, numbers is a parameter of integer data type to accept multiple arguments. In for loop, we're accessing every argument in numbers through x and displaying it in the output. With variable arguments, you can pass as many arguments as you want. Simple and flexible. Today, let's understand method overloading in Java, using a kitchen scenario. Method overloading allows creating multiple methods with the same name but different parameters. Imagine you have a method called makeJuice. MakeJuice can mean making juice from various fruits. We have different ways to make juice. Make juice with one fruit, like an apple. Make juice with two fruits, like an apple and an orange. Make juice with different quantities of fruits. When you need to perform similar tasks with different inputs, just like making different types of juice with the same method name, but varying ingredients. We use method overloading. Let's dive into method overloading in Java. Imagine calculating the area of rectangle, a circle, and a triangle using the same instance. Here's how we define it. In our shape class, we have 3 area methods. One for rectangles, one for circles, and one for triangles. For rectangle, we've 2 parameters, with length and width, and we are returning the calculated area here. For a circle, we have only one parameter as radius and returning the calculated area. Similarly for triangle, we have parameters as base, height, and Boolean value to check if it's a triangle, and returning the calculated area. In our main method, we are calling each method with the same name through the shape object with different parameters, and storing the returning value inside different variables. You can observe the code and the output. Imagine you have a set of Russian nesting dolls, each smaller doll inside a bigger one. This is similar to how method recursion works in Java. You solve a small piece of the problem first, and then call the same method to solve the next piece, layer by layer. In Java, a recursive method calls itself within its own code. Use recursion when your problem can be broken down into smaller, similar subproblems. Let's write a code to check if an array can be rearranged into consecutive numbers in Java. Our approach is to take an array as input and sort it from decreasing to increasing order. Then, we will compare each value from the previous value. We have to check two conditions while comparing. First, we will check for duplicates, and second, if the current number is not the next consecutive number. If these two conditions satisfies, we'll simply return false, because numbers are not consecutive. Let's dive into code. Inside the can-be-consecutive method, we are first sorting the taken as parameter. Once sorted, we are checking for duplicates using a for loop while comparing the next value from the previous value. At the same time, we are comparing if the next number is not one greater than previous number. If both conditions are true, the number is not consecutive, hence returning false. Else, once the loop completes successfully, the method returns true. Today, we will discuss about how we can reverse a string using method in Java. Reversing a string means that we will rearrange the characters of the string in the opposite order. Let's understand this with an example. Here, reverseString is a class with a reverse method that takes a string str, checks if it's null or empty using OR operator, and if not, reverses it using a string builder. The toString method is called to convert the string builder back to a string. The main method demonstrates the usage of the reverse method by reversing the string, follow us.java, and printing both the original and reversed strings. We know codes are simple sequence of instructions. But what if we want a code for a bigger model? Like a game. We simply don't want our code to get messed up. That's where comes object-oriented programming. OOP is all about organizing code around objects, just like real-world items. Like having different toppings on the pizza. You simply don't want your pizza to get messed up when you take one off or add another. Here, each topping is simply an object for the pizza. Similarly, this way of programming is centered around objects, helping organize code, making it more readable and reusable. Let's know about principles of OOPs. First is encapsulation, keeping data and methods inside a single unit, like a capsule. Think of a smartphone. You use apps without knowing their internal code. Encapsulation hides the complex parts and shows only what you need. Next is inheritance, when one class inherits properties from another class. Imagine a family tree. A child inherits traits from their parents, like eye color. In coding, a new class can inherit properties and methods from an existing class. Next is polymorphism, one name, many forms. Think of a remote control. The same button can control different devices. Finally, abstraction, simplifying complex systems by focusing on essential qualities. Imagine driving a car. You don't need to know how the engine works to drive. Abstraction means focusing on the high-level operations, like steering or accelerating. Now, let's break down a fundamental concept in Java: class versus object. Think of a class as a blueprint. Imagine you're designing a car. The class defines the car's attributes like color, model, and speed, as well as its behaviors like accelerate, brake, and turn. Now, an object is an instance of that class. When you build a car using that blueprint, you've created an object. So, when you see an actual Porsche driving down the street, that's an object created from the car blueprint. In Java, a class defines properties and methods, but objects are the real-world entities that interact with each other in your program. In Java, a class in programming is like a blueprint for creating objects. Imagine a class as a recipe for baking cookies. The recipe outlines the ingredients, attributes, and steps methods needed to bake the cookies. Let's understand class with a program. This is the student class. It has variables for roll number, name, course, and 3 marks M1, M2, and M3. The total method returns the sum of the 3 marks. The average method calculates the average by dividing the total by 3. The grade method returns A if the average is 60 or above, otherwise B. The toString method formats the student details into a string. In the student test class, we create a student object. We set the roll number, name, course, and marks. Finally, we print the total, average, details of the student. Data hiding is a principle of object-oriented programming where we restrict access to certain parts of an object to keep data safe and secure. Basically, restricting access to internal object details like some data and methods. Now, let's briefly compare data hiding with abstraction and encapsulation. Abstraction is hiding complex implementation details and showing only the necessary features. Encapsulation is bundling data and methods operating on the data into a single unit or class. While data hiding is restricting access to the internal state of an object. Let's take an example to understand better. Think of a car. You use the steering wheel and pedals without knowing the engine mechanics. That's abstraction. The car groups its components like engine, seats, and wheels into a single unit. That's encapsulation. The engine is covered and only mechanics can access it directly. That is data hiding. Let's talk about access modifiers in programming. Access modifiers control the visibility of class members, just like how different doors in a house control access to rooms. Imagine a community park. Only people within that community can enter. Similarly, default members are accessible within the same package. Think of a public library. Anyone can enter from anywhere. Similarly, public members are accessible from any other class. Picture a family heirloom. Only family members or close relatives can see it. Similarly, protected members are accessible within the same package and subclasses. Suppose it's your personal diary. Only you can read it. Similarly, private members are accessible only within the same class. Access modifiers control the visibility of a class, methods, and variables. Let's look at a simple program. Imagine a library system. We have a book class with different access modifiers. We have a title variable, which is private. This makes title accessible only within the book class, hiding it from other classes. Here, we can't access the title variable from main function. But when we make it public, boom. It is now visible globally, including other packages. This private variable can be accessed in the same class, using a method. And then you can call the method in main function. But we cannot access private instances in a subclass, that's inheritance. But when we make it protected, we can access it in any method including main function and in any subclass, but in the same package. We'll soon jump into packages. And when you don't specify any access modifier, it takes as a default. Any default instance is visible in the same package, but not in any other package. Today, I'll explain constructors in Java. Imagine, you just bought a new car. Before you can drive it, you need to set it up, adjust the steering wheel, mirrors, and seat. Similarly, in programming, a constructor is a special method used to initialize an object when it's created. Constructors ensure our objects start in a valid state. Without them, our car might not have seats or a working engine. Constructors in Java are essential for setting up objects with initial values, making sure they're ready to use right from the start. Whether it's a car, a person, or any object, constructors ensure everything is in place. Constructors are special methods used to initialize objects. Let's get into code. Imagine a car class. We have a constructor to initialize an object that takes no argument. All constructors must have the same name as the class. Here, it is a default constructor. Every time an object is created using the new keyword with no argument,
at least one default constructor is called. Like this. Next is parameterized constructors. By the name you must have understood. It allows you to set specific values for the object. In this example, we have created single parameterized constructor that takes the model as an argument. If we add another argument as year, it becomes double parameterized constructor. When you create a car object with arguments, this constructor is called.
Let's understand the constructor with a simple example. Here the class named as rectangle. These two lines declare two private member variables, length and width, both of type integer. Here, we take three methods of same name as class, but with different parameters. This is the default constructor for the rectangle class. It takes no parameter. This is a parameterized constructor that takes one parameter of integer type. This is also a parameterized constructor that takes two parameter of integer type. Then display method prints a string representation of the rectangle. In the main method, three rectangle objects are created. rect1 uses the default constructor, rect2 uses the single parameter constructor, and rect3 uses the two parameter constructor. Each constructor prints a message indicating which one is called, and the display method shows the dimensions of each rectangle.
This keyword in Java refers to the current instance of a class. It's used to differentiate between class attributes and parameters. Let's clear this with an example. We have a class person and a parameterized constructor to assign values. Here, we want to assign the parameters to the instance variables. But there's a problem. Name equals to name and age equals to age doesn't assign the parameters to the instance variables. They just assign the parameters to themselves. When we display the output, it gives null, because values passed by the object are not assigned to the instance variable in the display method. To fix this, we use the this keyword to refer to the instance variables. This.name and this.age refers to the instance variable here, and we are assigning parameters to the variables like this. Now, the constructor correctly assigns the parameters to the instance variables.
Let's understand the constructor overloading with a simple example. Here we have a class named constructor overloading, with three constructor of same name as class, a default constructor with no arguments, which sets x to 0 and name to default, a parameterized constructor with one argument, which sets x to the provided value and name to unknown, a parameterized constructor with two arguments, which sets x and name to the provided values. In the main method, we create three objects using each of the constructors and call the display method to print the values of x and name. This demonstrates constructor overloading, where multiple constructors with different parameter lists can be defined, and the correct constructor is called based on the number and types of arguments provided when creating an object.
Today, we are gonna create a box with 3 dimensions in Java. Let's jump in. Here's the box class with 3 constructors and a method to calculate volume. The first constructor sets all dimensions to 1 by calling the single argument constructor. The single parameterized constructor sets all 3 dimensions to the same value, creating a cube. The multiple parameterized constructor initializes the length, width, and height, making it a cuboid. Then there comes our method to calculate the volume. Let's test our box class in the main method. In our main class, we create 3 box objects using different constructors and print their volumes. Let's see the output.
There's a problem on class to create a bank account class with attributes account number, account holder's name, and balance, and methods to deposit and withdraw money. Let's jump into the code. In this code, it defines a bank account class with 3 attributes, account number, account holder name, and balance with private access and integer type. The constructor initializes these attributes. The class includes the deposit method increases the account balance by the specified amount and prints a confirmation message. The withdraw method checks if the balance is sufficient for the withdrawal. If so, it decreases the balance by the specified amount and prints a confirmation message. If not, it prints an insufficient balance. In the main class, we create a bank account object called MyAccount with an initial balance of $1,000. We display the account information using the display account in method. Then, we deposit $500 into the account and display the updated information. Next, we withdraw $200 and show the updated information again. Finally, we attempt to withdraw $1,500, which fails due to insufficient balance, demonstrating the balance check in the withdraw method. This example illustrates basic operations on a bank account using object-oriented programming.
Today, we're going to talk about arrays of objects in Java. In Java, an array is a collection of elements of the same type. What about collection of objects? Let's see how that works. Imagine you have a class called person. To create an array of person objects, you declare it just like you would with any other array. This line creates an array that can hold 3 person objects. But at this point, the array is just a container. We need to fill it with person objects. To initialize the array, you create new instances of the person class and assign them to each element in the array. Now, each element in the array holds a person object with specific data. You can access and use these objects just like you would with any other array. Let's continue the program on person class in array of objects. First, let's define our person class. This person class has 2 fields, name and age, a constructor to initialize the properties and a method to display the information. Now let's move to our main class. Here, we create an array to hold person objects. Then, let's initialize each element with a person instance while passing name and age to the array position. Then, we use a loop to iterate over the array to display each object details. Here, you can see the output. Inheritance is a fundamental concept in object-oriented programming that allows one class to inherit fields and methods from another class. It helps to create a hierarchy of classes and promotes code reuse. Think of it like a family tree. You have a base class, often called the parent or superclass, and derived classes, known as child or subclasses. You can inherit from a class using the extend keyword like this. Let's understand inheritance with a simple example. Here, we start by defining a class named animal. Inside this class, there's a method called owner. Next, we define another class named dog that extends animal, meaning it inherits its properties and methods. In the dog class, we add a new method called bark. Now we have our main class, Java inheritance, with the main method where the execution begins. Inside the main method, we create an instance of the dog class. We call the bark method on this dog instance. Then we call the owner method, which the dog class inherited from animal. This prints a barking. And the dog owner is the Java heir to the console. And that's how inheritance works. Let's understand class with an example. In this code, we have an animal class with basic properties and methods. We also have 2 subclasses, dog and cat, which extend animal. Both subclasses override the sound method to provide their specific sounds. The dog class makes the dog bark, and the cat class makes the cat meow. In the main class, we create instances of dog and cat, but reference them with the animal type. This demonstrates polymorphism, where the sound method called on the animal reference executes the overridden method in the dog and cat classes. To call subclass-specific methods like fetch, for dog, and climb, for cat, we use the instance of operator to check the object's actual type. If the check passes, we cast the animal reference to the specific subclass type and then call the method. This code highlights the power of inheritance and polymorphism, allowing objects to be treated as instances of their parent class while still accessing subclass-specific behaviors. Let's understand about constructors in inheritance. We have here a parent class with a default constructor, and a child classes that is inherited from parent class. This class has a default constructor too. Now let's understand the constructor calling. In our main method, when we create an object of parent class, it simply calls the default constructor of parent class like this. But what if we create an object of child class? Give it a thought. Let's see what we get. Here, we got both parent constructor and child constructor message. Both constructors are executed even if we just call the constructor of child class. This is because, when we create an instance of the child class in our main method, Java automatically calls the parent constructor before the child constructor. This ensures that the parent part of the object is initialized before the child part.
Let's understand super keyword in Java. Imagine a bakery where a parent class, baker, makes bread. The child class, pastry chef, extends baker but also makes pastries. Sometimes, the pastry chef needs to call the baker's method to make bread before making a pastry. Super.bake in pastry chef calls the bake method from the baker class, ensuring the bread is baked before the pastries. This is how the super keyword helps access the parent class's methods and constructors in Java. Inheritance is a core concept in Java that allows a class to inherit properties and methods from another class. There are several types of inheritance. First up, we have single inheritance. This is where a class inherits from just one superclass. This is how the syntax goes of single inheritance. Next, we have multilevel inheritance. A class inherits from another class, which in turn inherits from another class. Here, you can see the syntax and differentiate. Then there's hierarchical inheritance. Multiple classes inherit from the same superclass. Like a tree. Here, both child 1 and child 2 are inherited from a single superclass. Java doesn't support multiple inheritance directly. This is when a class would inherit from multiple classes. Instead, Java uses interfaces to achieve similar functionality. We'll see that in coming videos. Let's understand about multilevel inheritance in Java with a simple example. Imagine a transportation hierarchy: vehicle, car, and electric car. Let's jump into code. First, we have the vehicle class with a method move that prints vehicle is moving. Next, the car class inherits from vehicle and overrides the move method to print car is moving. Finally, the electric car class inherits from car and overrides the move method to print electric car is moving silently. When we create an instance of electric car and call move, it uses its own method, showcasing how each level can build upon and customize behavior from previous ones. This hierarchical structure in Java helps organize and reuse code efficiently, just like evolving features in vehicle technology. Hierarchical inheritance is when multiple classes inherit from the same superclass. Let's dive into it with a basic program. First, we have a student class. Both undergraduate and graduate will inherit from this class. The student class has fields for name and age and a method displayInfo to print student details. Next, we have the first child class, undergraduate, that extends student. This class displays the major of the student. Then we have the second child class, graduate, that also extends student. Graduate inherits name, age, and displayInfo from student and has its own field research topic and method display research topic. Finally, let's create instances of undergraduate and graduate in our main method and call their methods. When we run this code, both undergraduate and graduate can access the displayInfo method from student, along with their own methods. Let's understand method overriding in Java using a simple example. Method overriding in Java is like inheriting family traditions. Imagine you have a family recipe for spaghetti. Your grandmother made it one way, and that's the original recipe. Your mom learned it from her, but she adds her twist by using a special sauce to give it more taste. Now you've learned it from your mom, but you prefer to add extra spices. Each generation retains the essence of the recipe but changes how it's made to fit their taste. Similarly in Java, a child class can use a method from its parent class but modify its behavior to suit its needs. This is called method overriding. Today we're taking a popular LeetCode problem, best time to buy and sell stocks 1, which has been majorly asked in Goldman Sachs and Google. You're given an array of stock prices where each element represents the price on a given day.
Your goal is to maximize your profit by buying on one day and selling on a different day. Let's take an example. Buying on day 2 and selling on day 5 gives the maximum profit of 5. If no profit can be made, we return 0. Let's jump into our approach. If we can compare these values in an array somehow, we can find the best day to buy and sell the stock. Here's what we're gonna do. Let's assume we are buying on the first day for now. Then we are gonna compare each value in the array. If the next price is lower than the buy price, we should change our buying date. And meanwhile, if the next value is greater than the current buying price, we should check for selling for a good value. And sell for the highest amount. Let's code. We initialize buy with the first day's price and profit with 0. We loop through the prices starting from day 2. If the current price is lower than buy, we update buy. If the difference between the current price and buy is greater than profit, we update profit. By the end of the loop, profit will hold the maximum profit possible. If no profit can be made, it will return 0.
Previously, we understand method overriding in Java with an example of spaghetti recipe. Let's understand how we can write the code in Java. In this code, we will have 3 classes. The first class is the grandmother class, has a method makeSpaghetti, which prints making spaghetti with the original recipe. The mother class extends grandmother and overrides makeSpaghetti to print making spaghetti with a special sauce. Similarly, the myself class extends mother and overrides makeSpaghetti to print making spaghetti with extra spices. In the family recipe class, we define the main method, which is the entry point of the program. We create objects for grandmother, mother, and myself class. When we call makeSpaghetti on each object, it prints the respective version of the recipe. Method overriding allows a subclass to provide a specific implementation of a method already defined in its superclass. First, let's start with the do's. Using an override helps catch errors at compile time if the method signature doesn't match. Also, use super to call the superclass method if you want to extend its behavior. Under the don'ts. Overriding methods should have the same signature as the method in the superclass. Changing the parameters will not override the method. An overridden method should not have less visibility than the method in the superclass. For example, you can't override a public method with a protected one. This will cause a compile time error. What do you mean by polymorphism in Java? Polymorphism in Java is like having a universal remote control that can operate multiple devices. Imagine you have a universal remote that can control your TV, air conditioner, and sound system. Let's see how this works in Java code. First, we have a base class called device with a method operate. Then we have specific classes for TV, air conditioner, and speaker that extend device and override the operate method. In the main method, we can create a reference of type device and assign it to different device objects. Here, the operate method is like pressing a button on the remote. Even though it's called on different devices, each device responds in its own way. This is the power of polymorphism. One interface, multiple implementations. Imagine you're creating a program to model different types of bank accounts and their interest calculation methods. Let's get into code. Let's create a base class called BankAccount first. BankAccount has a method calculate interest. Next, we have the savings account class, which is inherited from BankAccount class. This overrides the calculate interest method to provide its specific implementation into interest rates. Then we have the current account class, which also extends BankAccount and overrides the calculate interest method to provide its specific implementation into its interest rates. Finally, let's see how we can use these classes. In the main class, we create instances of savings account and current account as bank account objects, and call their calculate interest methods. You can differentiate with the help of output. Imagine you're a teacher. You have different types of students, school students and college students. Both need to study, but in different ways. In Java, you can create an abstract class called student to represent this. You can't make a student directly because it's too general. Instead, you use it as a template. High school students and college students will be specific classes that inherit from student. They'll each have their own way of studying but still follow the basic idea. So an abstract class helps you define a general structure and enforce certain methods that subclasses must implement, ensuring consistency while allowing flexibility. Previously, we understand what is abstract classes. Let's understand with a simple example through a code. In our code, we have an abstract class shape with an abstract method draw. This means every shape must have a draw method, but we don't specify how it works. Next, we have two classes, circle and square, that extend shape and provide their own implementations of the draw method. In the main class, we create objects of circle and square, and call their draw methods. This demonstrates how an abstract class enforces a method contract while allowing subclasses to define their specific behaviors. Imagine you're building a payment process. Today we're tackling a popular LeetCode problem, valid palindrome, which is majorly asked in Google, Spotify, and many other companies. So what's a palindrome? Anything that reads the same backward and forward. Here, we have to check if the given phrase is a palindrome or not. A phrase is a palindrome if, after converting all uppercase letters into lowercase and removing non-alphanumeric characters, it reads the same forward and backward. Given a string, return true if it is a palindrome, or false otherwise. Let's code. We have string s as function parameter. Before lowercasing, we have to remove all non-alphanumeric characters and then convert to lowercase. Then initialize two pointers, start and end, pointing to the starting and ending of the string respectively. Then we'll use a while loop to compare characters from both ends towards the center. If the characters at start and end don't match, return false. Otherwise, move the pointers inward. If all characters match, return true. And that's it. What do you mean by interface in Java? Imagine a music app where different devices like phones, tablets, and smart speakers can play songs. In this app, there's a common play music feature, but each device might do it differently. An interface in Java is like a blueprint for this feature. It defines what actions should be available, like play, pause, and stop, without specifying how each device should perform these actions. Just like the app ensures every device can play music, a Java interface ensures that any class implementing it will provide the necessary functionalities, even if the implementation details vary. Interfaces allows us to define methods that must be implemented by any class that uses the interface. Let's see how it works. We have an animal interface that defines a method makeSound which any implementing class must provide. Next, we have the dog class that implements the animal interface. Here, dog implements animal and provides the specific implementation of the makeSound method. Finally, let's see how we can use these in our main class. In the main class, we create an animal reference pointing to a dog object and call its makeSound method. That's it. You can see the output. Let's understand the difference between interface and class. An interface is defined as the abstract type used to specify the behavior of a class. Interface in use to achieve abstraction and multiple inheritances. An interface contains static constants and abstract methods. What we know about classes. It can have both abstract and concrete method. It can also have constructors. A class can extend only one abstract class due to single inheritance. Here, abstract class with abstract method which extends with me-class. Next, in interface all interface are abstract by default, but can have default and static method. Interface cannot have constructors. A class can have multiple interfaces. Here abstract method called by default and me2 class implements the base. This is what class versus interface. In Java, a class can inherit from multiple interfaces to achieve multiple inheritance. Let's see how it works with a basic example. Here's our first interface flyable. Flyable defines a method fly which any implementing class must provide. Next,
we have the swimmable interface. Swimmable defines a method swim which any implementing class must provide. Now, let's create the duck class that implements both flyable and swimmable. Note that here implements keyword is used in place of extends keyword. Duck implements both flyable and swimmable interfaces, providing the specific implementations for the fly and swim methods. Finally, let's see how we can use these in our main class. In the main class, we create an instance of duck and call its fly and swim methods. That's it. You can see the output.
Let's understand interface with an example. Consider an interface called animal with methods like eat and sleep. Different classes like dog and cat implement this interface, providing their own versions of these methods. For example, dog might implement eat by printing eats kibble and sleep by printing a dog sleeps soundly. Similarly, cat could have its own implementations. The main method creates instances of dog and cat, then calls their eat and sleep methods, demonstrating how each class implements the animal interface differently. By using interfaces, you can ensure that all implementing classes provide the same set of methods, but each class can define the behavior differently. This promotes flexibility and code reusability.
Let's create a robot that can move and store items. Let's code. We'll create two interfaces, movable and storable, and a class smart robot that implements both. Movable defines a method move which any implementing class must provide. Next, we have the storable interface that defines a method store which any implementing class must provide. Now, let's create the smart robot class that implements both movable and storable. Smart robot implements both movable and storable interfaces, providing the specific implementations for the move and store methods. Let's add some additional functionality to smart robot to demonstrate its versatility. Now smart robot has a battery level and checks it before moving. It also has a method to display the battery level. Finally, let's see how we can use these in our main class. In the main class, we create an instance of smart robot with a battery level of 100, move it, store an item, and display the battery level. That's it. Here is our digital robot.
Let's understand more with do's and don'ts of interface. First, DOUs interfaces for multiple inheritance. Ideal for when a class needs to adopt functionalities from multiple sources. Second, implement interfaces in your classes. Ensure classes provide concrete implementations for the methods defined in the interface. Third, use interfaces to define common behaviors. Great for specifying a contract that multiple classes can adhere to, enhancing flexibility. Fourth, prefer interfaces for loose coupling. Keeps your code modular and easier to maintain by reducing dependencies between classes. Next, don'ts. First, use interfaces for implementation details. Interfaces should only declare methods, not define how they should work. Second, include state in interfaces. Interfaces should not have instance variables. They should only declare methods and constants. Third, use interfaces as a replacement for abstract classes. Use interfaces for defining roles, not for providing a base class with common functionality.
Let's take a really simple problem today. Search insert position. Given a sorted array of distinct integers and a target value, we need to find the index of the target. If the target isn't in the array, we should return the index where it would be if it were inserted in order. We can solve this with big O of log n runtime complexity. Let's take an example. Here target 5 is present in index 2. So we should return it. Next, target 2 isn't present here, but if it was, it should have been present in index 1. So return it in this case. We can use binary search method to divide the problem into half. If our target is present in either of the side, we divide that side again and check with the same process. Let's dive into the solution with binary search method. We initialize left to 0 and right to the last index of the array. We use a while loop that runs as long as left is less than or equal to right. Inside the loop, we calculate the middle index mid. We check first if mid is equal to the target. If mid is greater than target, we divide the problem into left side, while making right equals to mid minus 1. If mid is less than the target, we make left equals to mid plus 1. If we exit the loop, it means the target isn't found, and we return left.
Do you know what is inner classes in Java? Think of a house, which represents a class in Java. Inside the house, there's a thermostat that controls the heating system. The thermostat is an inner class. It doesn't make sense outside the context of the house because it's designed specifically to manage the house's temperature. The house outer class includes rooms, windows, and doors, while the thermostat inner class manages the heating. The thermostat needs the house's infrastructure to function, showing how inner classes in Java work. They are tightly coupled with their outer classes, making the overall system more organized and manageable.
Today, we're diving into the different types of inner classes in Java. First up, we have the nested inner class. It's a class within another class, used to logically group classes that are only used in one place. Imagine we have a class car with an inner class engine. We create an instance of engine using an instance of car. This helps keep the engine class tightly coupled with car. Next, we have method local inner classes. These are defined within a method and can only be accessed within that method. Let's look at a method inside a class outer where we define a method local inner class inner. Here, inner class can only be used within the display method. Now, let's talk about static nested classes. These are static classes defined inside another class, and they can access static members of the outer class. Here's a static nested class example inside an outer class. Since inner is static, it can access static members of outer without needing an instance of outer. Lastly, we have anonymous inner classes. These are used for instantiating classes that may be used only once. It's like creating a subclass and instantiating it all in one step. Here's an example using an anonymous inner class to create a one-time implementation of an interface greeting. This is handy for quick and concise implementation.
Let's understand the concept of nested inner loop in Java. These are classes defined within another class, providing better encapsulation and logical grouping. First, why nested inner loop is used. You'd use nested inner classes when you want to logically group classes that are only going to be used in one place. Second, when nested inner loop is used, when you want to keep your code organized and readable. Plus, inner classes can access all members of the outer class, including private ones. Let's look into the code. We have an outer class with a private integer outer value set to 10, and an inner class inside it. The inner class can access outer value and print it using the display method. Now in the main class, we create an instance of outer class. Then using this instance, we create an instance of inner class with outer.newInnerClass. Finally, we call inner.display, which prints the outer value from the outer class. And that's it. Nested inner classes help you keep related classes together and allow access to the outer class's members.
Today, we're diving deeper into nested inner classes in Java. First, let's see how a nested inner class can access private instance variables of the outer class. Notice how inner can access the private variable data directly. This is because an inner class has full access to the members of its outer class. Next, let's talk about nested interfaces. Did you know an interface can also be nested within a class and have access specifiers? The nested interface is private, and only the inner class inner can implement it within the outer class. Now, let's see how the Java compiler handles nested inner classes. On compiling a single class, Java just creates compiled class file for that. But when you compile a class with an inner class, the compiler creates separate files for the outer and inner classes. For example, if you have a class outer with an inner class inner, the compiler generates two class files, outer.class and outer$inner.class. This naming convention ensures that the inner class is associated with its outer class, but still treated as a separate class file by the compiler.
Now, we will understand the concept of method local inner class. It defined within a method of an outer class. This type of inner class has access to the fields and methods of its enclosing class, and also to the final local variables of the method. So when it is used, method local inner classes are used when you need to logically group a class with a specific method, and you don't need to use the class outside of that method. And how it is used. A method local inner class is defined and used within the scope of a method. It can be instantiated, and its methods can be called within the same method. Now, let's get into the code. In outer class, a private string outer field is initialized with outer field value. Next in display method, a final string local variable initialized with method local variable. Next method local inner class, which is defined inside display. A inner display method inside method local inner class that prints the values of outer field and method local variable. An instance of method local inner class is created, and its inner display method is called printing the values. Then a main method creates an instance of outer class. Calls the display method on this instance. This setup is useful when you want to encapsulate helper functionality within a method, keeping the class scope limited to the method itself.
Today, we're diving into static inner classes in Java. It's a nested class that's marked with a static keyword. Here's a simple example with a class outer and a static inner class, static inner. You can instantiate static inner without creating an instance of outer. Like this. This is useful when your inner class doesn't rely on the instance of the outer class. Now, a key point. A static inner class cannot access non-static members of the outer class directly. Check this out. Because static inner is static, it can't access data directly, since data is a non-static member of outer. However, you can pass an instance of the outer class to access its non-static members. This way, you pass an instance of outer to static inner to access non-static members.
Do you know about anonymous inner class? An anonymous inner class in Java is a type of inner class that doesn't have a name. It is used to define and instantiate a class simultaneously, and is often used for implementing interfaces. Syntax of anonymous. We can create a new anonymous inner class after creating an object of a class that contains the method. Do not need to use a class keyword with an anonymous inner class. E just starts with braces and contains the method. Anonymous inner class starts just the creation of an object and ends with a semicolon of that object. Let's get into the code. Here, a class A is defined with a method show that prints in a show. The demo class contains the main method where execution starts. Inside the main method, an instance of A is created using an anonymous inner class. This overrides the show method to print in new show. obj.show is called, which invokes the overridden show method printing in new show. The main point is that the anonymous inner class overrides the show method in class A, demonstrating polymorphism in Java.
Today, we're diving into more about anonymous inner classes in Java. These are super useful for creating quick, one-off class implementations. It's a type of inner class without a name, used to instantiate objects. Here's a basic example using an interface. Notice how we create an instance of greeting and override its method without naming the class. Anonymous inner classes are also handy for implementing abstract classes or interfaces on the spot. Here's another example with an abstract class. We create an instance of animal and provide an implementation for the makeSound method without subclassing animal. That's it. Let's create a program for a digital library that contains the concept of inner classes. Let's see in code. We have library as our outer class, and book is the inner class. The book class can access the private instance variable library name from the outer class. And we have a constructor in the outer class to initialize it. Next, the inner class has its own variables and methods. In the book class, the displayDetails method can access the library name from the outer class. This is one of the powerful features of inner classes. Let's take a whole look on our code. In the main method, we create an instance of library, and then an instance of the inner class book, using the outer class instance. We then call display details to print the book details.
What do you know about static in Java? In Java, static refers to a keyword that can be applied to variables, methods, and nested classes. When something is declared static, it belongs to the class itself rather than any instance of the class. Imagine a library. The library building and its address are static. They don't change based on who visits. Similarly, static variables and methods are shared among all instances of a class. For example, a static variable could track the number of books in the library, accessible and modifiable by any visitor. Static methods, like a method to get the total number of books, can be called without creating an instance of the library. A static nested class is like a specific section in the library dedicated to a genre. We use static when we need shared data or behaviors across all instances, like configuration settings or utility functions, to avoid redundancy and save memory.
First, what is a static variable? It's a variable that's shared among all instances of a class. This means there's only one copy of the variable, no matter how many objects you create. Let's understand through code. Here, we have a class counter with a static variable count. There is a display counter method to display the total count. This variable is shared among all instances of counter. In main, if we call the method every time after using a new object. This is the output. The count variable remains the same throughout the code, so we see the value get increment where the previous object has left. But when we remove the static keyword from our count variable and call it using the same three objects, this will be the output. Here, every object is calling a new instance of count variable, and hence it doesn't catch up with the whole code. Now you can differentiate clearly. So use static variables for data that's common to all objects, but be cautious as they can introduce dependencies that are hard to manage in large projects.
Today, let's understand static method in Java. A static method belongs to a class, not an object. You can call it without creating an object. When to use reusable actions like calculations, formatting, etc. Method that don't need object-specific data. Methods related to the class itself, not its instances. Now, let's get into code. Public static int add int a in b. This line declares a public static method named add that takes two integers as input and returns an integer. Return a plus b. This line calculates the sum of a and b and returns the result. So, static methods are class-level tools, handy for utility functions or actions independent of object state.
Today, we're diving into static blocks in Java. Static blocks are special blocks of code that get executed when a class is loaded into memory, even before the main method runs or any objects are created. They're perfect for initializing static variables or executing code that needs to run just once, before anything else in the class. Let's look at this simple code example to understand how static blocks work. Here, we have a class test with two static blocks. These blocks of code will execute in the order they're written when the class is loaded, even before we create an object or enter the main method. Now, let's see what happens when we run this code. Main gets printed from the main method. And since we create an object of test after that, the static blocks run again. But remember, static blocks only run once per class load. The first time it's triggered is when the class is first loaded.
Let's learn about final keyword in Java. Imagine your car's odometer. Once it hits a certain mileage, that number is fixed. You can't change it. Here's the syntax: final int odometer reading equals 12,345. In Java, a final variable is like that odometer. Once you give it a value, it stays that way forever. You can't change it later. It's used for values that should never change, like mathematical constants or configuration settings. This helps prevent accidental changes and makes your code more reliable.
Today, we're breaking down a cool Java program that shows off the power of the static keyword. First up, let's define a static variable. Remember, Static variables are shared across all instances of a class. Here, TotalBooks is a static variable. It keeps track of the total number of books in all libraries combined. Next, let's create a static method. This method can directly access our static variable. The addBooks method updates our TotalBooks count by the number of books added. Now, let's use a static block to initialize or configure settings before any objects are created. This static block prints a message when the class is first loaded into memory, letting us know the library system is ready. Let's put it all together in the main method and create some instances of the library class. Here we create 2 library instances and use our static method to add books to our total. Notice how TotalBooks keeps track of the total across all libraries. You can see the output.
Let's understand what's the specialty of final in Java. First, final variable, which value cannot change after initialization. Often used for constants. Convention, capital letters. Second, final method, which cannot be overridden in subclasses. Ensures method behavior remains consistent. Third, final class, which cannot be extended. Protects class integrity. Example, string class. Hence, final in Java ensures immutability for variables, methods, and classes, preventing modification and inheritance.
Let's dive into final methods in Java. In Java, marking a method with a final keyword means, hey, you can't override me. But why would you do that? You use final methods when you want to prevent subclasses from changing the method's behavior. This is great for ensuring that critical functionality stays intact, like a method that calculates a crucial business rule. Here's a quick example. We have a class bank account with a final method, calculate interest. This method is locked. Let's see what happens if someone tries to override it in a subclass. Here's a subclass trying to override calculate interest. Oh, we get a compile time error. Java says no. The final method stays unchanged. So use final methods when you want to lock in critical behavior and avoid surprises. Simple, right?
Let's understand final class in Java. India, our great nation, is like a final class in Java. It's completely entity, a foundation upon which many things are built, but it cannot be further extended or modified. Just like India's sovereignty is inviolable, a final class is unchangeable. It's a blueprint for objects, but no other class can inherit its properties. Here's a small code. This India class represents our nation. It has its own unique attributes and methods. But we cannot create a new India class that extends India. Trying to inherit from India would be like trying to change the fundamental structure of our nation. It's possible and incorrect. Just as India is a standalone proud entity, so is a final class in Java.
Today, we're diving into the final keyword in Java with a cool program example. We'll see how final can be used with variables, methods, and classes. Let's start by creating a class called bank account. We're going to secure some crucial parts of our class using the final keyword. Here's what's happening. Final class bank account means this class cannot be extended. Final string account number ensures the account number can't be changed once it's set. The final void deposit method can't be overridden by any subclass. These are the helper methods. Pause to read it. Let's see this class in action by creating an instance of bank account and performing some operations. We create a bank account with an initial balance of $1,000. We then deposit $500 and withdraw $200, with the balance being updated accordingly. Notice that trying to change the account number will throw a compile time error because it's final.
What do you understand by singleton class in Java? You only want one jar for everyone. A singleton class is like that. It ensures only one instance exists. First, why to use? Control access to shared resources like database connections. Avoid unnecessary object creation, saving memory. Provide a global point of access for a shared object. Second, how it works. Private constructor prevents direct object creation. Static private instance holds the single object. Public static method returns the instance, creating it if needed. Let's get into the code. Here, private static singleton instance, a static variable to hold a single instance of the class. It's private to prevent external access. Private singleton, a private constructor to prevent direct object creation outside the class. Public static singleton getInstance. This is the public method to get the instance. Checks if instance is null, first time called. If null, creates a new instance and assigns it to instance. Returns the instance. This code guarantees only one instance of the singleton class can exist. The getInstance method is the only way to access it, ensuring controlled access.
Today, we're diving into a program on singleton class. A singleton class in Java ensures that only one instance of the class exists throughout the application. It's like having a single remote control for your television. Here is our program. First, we declare a private static instance of the class. This static variable will hold our single instance. Next, we make the constructor private. This prevents other classes from creating new instances directly. The singleton class is the only one that can create itself. The key to the singleton pattern is this getInstance method. It checks if an instance already exists. If not, it creates one. If it does, it simply returns the existing instance. Let's see it in action. In your main method, when you call getInstance and invoke showMessage, you'll always interact with the same singleton instance. As you can see, even though we called getInstance twice, only one instance was created. That's the power of the singleton pattern. Use it when you need one and only one instance of a class throughout your application.
What do you know about packages in Java? Imagine your room is a mess. Clothes, toys, and books everywhere. Now, imagine organizing everything into boxes. That's what packages do for your Java code. Packages are like special boxes that hold related classes and interfaces. They keep your code tidy and easy to find. For example, the java.util package has handy tools like a calendar or a list. Java looks inside these packages when you need to use a class. It's like searching for a toy in the right box. Packages prevent confusion and make your code efficient.
Let's learn how to create a package in Java manually. First, open your favorite IDE. Here I have opened my VS Code in my system. Open any folder. Here I have just opened my .vs Code in my system. Then let's create a package first. I named my package as my Java practice. Here, you can collectively store your class files, Java files for a single project. Let's just create a file for basic demonstration, and create our main file for executing our student.java file. Let's write our first statement of our student.java file. Package my Java practice semicolon. This line demonstrates that this student class belongs to this package. Let's do the same to our main file. Now both the files belongs to the same package. Let's write a simple code for understanding. Now, let's execute our main file. You can see the result. This is how you can use packages to keep your code modular and organized.
Let's understand package naming conventions with do's and don'ts of package. In the world of software development, packages are the building blocks that organize our code. A well-chosen naming convention for your packages can significantly improve code readability, maintainability, and collaboration. Now, let's go for do's of package. First, use lowercase letters. This is a common practice in most programming languages. Second, separate words with underscores. This enhances readability. For example, my_package. Third, Be descriptive. The name should reflect the package's purpose. Fourth, avoid generic names. Names like util or common can become ambiguous. Don'ts of package. First, use capital letters. This can lead to inconsistencies and confusion. Second, use hyphens or spaces. These characters can cause issues in certain programming languages. Third, use abbreviations. While they might save space, they can make the code harder to understand. So the next time you're structuring your project, remember to choose package names that are clear, concise, and consistent. Today, we're diving into access modifiers in Java and how they work across different packages. First up, public. Whether it's in the same class, a different class, or even in another package, public access has no restrictions. Next, we have protected. Protected members are accessible within the same package and also in subclasses, even if they're in different packages. This is super useful for inheritance. Private means private. It's the most restrictive access modifier. If you declare something as private, it can only be accessed within the same class. Not even subclasses or classes in the same package can access it. Finally, there's default, which is when you don't specify any access modifier. Default access allows members to be accessible only within the same package, but not outside of it. So in summary, public is everywhere, protected is within package and subclasses, private is within the class only, and default is within the package. Understanding these will help you design your classes with a right level of access control. Today, we're diving into the world of Java's predefined packages. These are ready-made collections of classes that provide essential functionalities. Let's start with the object class. It's the parent of all classes in Java. Think of it as the grandparent of the entire Java object hierarchy. Next up, we have wrapper classes. These classes wrap primitive data types, like int, double, etc., into objects. Why do we need this? Well, it allows us to perform object-oriented operations on primitive values. Finally, let's explore the math class. This class is a treasure trove of mathematical functions. Need to calculate square roots, trigonometric values, or random numbers? The math class has you covered. So the next time you're coding in Java, remember these predefined packages. Today, let's dive into the backbone of Java, the object class. It's the parent of all classes in Java. In other words, every class you create automatically inherits from the object class. Even if you create a simple class, it will still inherit the object class and has access to all its methods. But why is this important? The object class provides essential methods that every Java object can use. For example, you can override toString method to print custom object details. Here, we override the toString method to customize the output when printing our object. Try experimenting with these methods. What do you know about exception handling in Java? Imagine a trip, a smooth path, a clear destination. But what if you encounter an unexpected obstacle? In programming, this unexpected obstacle is called an exception. It's an error that disrupts the normal flow of a program. Cause of exception. Exceptions can arise due to various reasons, such as invalid user input, file not found, network errors, division by zero, out-of-memory errors. Next, why should we handle exceptions? Handling exceptions is crucial for 1. Preventing program crashes. 2. Providing informative error messages. 3. Maintaining program stability. 4. Ensuring graceful recovery from errors. Imagine you're trying to open a file. If the file doesn't exist, an exception is thrown. By handling this exception, you can display a message saying "file not found" instead of the program crashing. Exceptions are a natural part of programming. By understanding and handling them effectively, you can create more robust and reliable applications. Let's see how to handle those unexpected errors that can crash your code. Imagine you have a division problem in your code, but you try to divide by zero. Dividing any number by zero is undefined in mathematics. In Java, it throws an arithmetic exception. Let's look at the code. Running this code will give you an error and crash your program. This line throws the main exception.
But don't worry, we can handle this gracefully using try-catch blocks in next video.
Let's try to understand try and catch block in Java. Imagine you're a chef trying to make a new dish. You have a recipe that involves several steps, including chopping vegetables, mixing ingredients, and baking in the oven. The try block. This is like following the recipe step by step. You're doing everything as instructed, hoping for a delicious outcome. The catch block. This is your backup plan. If something goes wrong, like cutting your finger while chopping vegetables or burning the dish in the oven, the catch block is there to handle the situation. For example, if you accidentally cut yourself while chopping, the catch block might involve stopping the process, immediately stopping the recipe to prevent further injury, addressing the issue, cleaning the wound and applying a bandage. Here's a syntax. The try block contains code that might throw an exception. If an exception occurs, it's caught by the catch block, which specifies the type of exception and provides a way to handle it.
Hey everyone! Today we're solving a cool LeetCode problem, Robot Return to Origin. Ready to take on the challenge? Let's dive in. In this problem, you control a robot on a 2D grid. The robot starts at origin. You're given a string of moves, like U4 up, D for down, L for left, and R for right. Your task is to determine if, after executing all these moves, the robot ends up back at the origin. Let's take an example. Following the input string, moving up, then down, then left, and then right, the robot comes back to the starting point. In the next example, the robot moves up twice and left once, which doesn't bring it back to the origin, so return false. To solve this problem, we need to keep track of the robot's position on the grid. Let's see in code. We start with x equals 0 and y equals 0, representing the origin. We loop through each character in the move string and update our x and y values accordingly. Finally, we check if x and y are both 0. If yes, the robot is back at the origin, so we return true. Otherwise, false.
Let's understand nested try and catch block with a simple program. Public class NestedCatch defines a public class named NestedCatch. Int a equals 30, 20, 10, 40, 0. Creates an integer of array a with 5 elements. Begins a try block, where code that might throw exceptions is placed. Int c equals a0/a4 tries to divide the first element of a30 by the last element, 0. This will throw an arithmetic exception as division by 0 is not allowed. System.out.println, division is plus c. If the division is successful, which it won't be in this case, it will print the result. Begins another try block nested within the first. System.out.println a5 tries to access the sixth element of a, which is out of bounds, causing an array index out of bounds exception. Catch array index out of bounds exception e. Catches the array index out of bounds exception thrown in the nested try block. System.out.println index is invalid. Prints a message indicating that the index is invalid. Catch arithmetic exception e. Catches the arithmetic exception thrown in the outer try block. System.out.println denominator should not be 0. Prints a message indicating that the denominator cannot be 0. System.out.println by prints a final message. Let's understand checked and unchecked exceptions in Java. Suppose in a restaurant kitchen chef trying to open a recipe book. Where's that recipe book? I can't find it. Assistant, oh no, it's a checked exception. We can't proceed without the recipe. So, checked exceptions. These are exceptions that the compiler forces you to handle. They are typically caused by external factors beyond your control. Example, file not found exception. If a file is not found. In other scenes, suppose a customer at the restaurant, saying after taking a bite of food, "Ouch, this steak is raw." Waiter replying, "I'm so sorry. That's an unchecked exception. I'll get you a new one right away." So, in unchecked exceptions, these are exceptions that the compiler does not force you to handle. They are typically caused by programming errors. Example, null pointer exception. If you try to access a null object.
Today, Let's clear up the difference between throw and throws in Java. First up, throw. Throw is used to manually throw an exception in your code. Like saying, I see a problem here, I'm raising an exception. Here we're throwing an illegal argument exception if something goes wrong, like invalid input. Throw is usually used inside a method or block of code. Next is throws. Throws is used in the method declaration to indicate that the method might throw an exception. It's like a warning sign, this method might throw an exception, be ready to handle it. Here, throws IO exception tells the caller, hey, this method might throw an IO exception, handle it properly. Let's see a quick example of both throw and throws in action. In the method checkAge, we use throws exception to declare that this method may throw an exception. Inside the method, if age is less than 18, we use throw to manually throw an exception with a message, you must be 18 or older. In main, we call checkAge 15, which triggers the exception. The catch block then catches and prints the exception message.
We're going to explain how exceptions work in Java by walking through a simple example, where we calculate the area of a rectangle but handle potential errors. Let's jump right into the code. We've got a class negative dimension exception that extends the exception class. This is a custom exception that will be thrown if we try to pass negative dimensions when calculating the area of a rectangle. This custom exception prints a specific error message when triggered. Now, we have a method area in our throws demo class. It takes two arguments, length L and breadth B, and checks if either of them is negative. If either L or B is negative, it throws our custom exception. Otherwise, it returns the area by multiplying length and breadth. Here's the method meth1 that calls the area method. Meth1 is a simple method that just calls the area method with positive dimensions. Here 10 and 5, so no exception will be thrown in this case. Finally, we've got our main method where all the magic happens. The main method uses a try-catch block. It calls meth1, and if any negative dimension exception is thrown, the program catches it and prints the error message. At the end, we print hi to the error stream. And that's it. We've successfully handled a potential error in our program with a custom exception in Java.